Okay, here's theorem 31. It uses theorem 30 as part of it. So you've got a function that maps from A to B, just two sets, and this you're told that this function is bijective. Okay? And there's a function g which maps B back to A, and it has these properties, right? So g of A is A and f of g of B is B. Okay? So in a sense, the f now is the inverse of g. Okay? So the theorem says that this g with these properties has two properties, this g. It's bijective and it's uniquely determined by f. Okay? So there's, in effect, there's only one g that's the inverse of f. Okay, how to prove that? Well, the first part is pretty easy, given that we have the result of theorem 30. Now, can you remember the essence of what theorem 30 was saying? It was an if and only if, so both ways, left to right, right to left. If your f is bijective, then there's a g that is the inverse. Okay? Now, here, in a sense, you could say the f is acting as the inverse of g. So you can reverse the roles. So in the previous theorem, instead of having f, you have g. Instead of having g, you have f. And so you can conclude that because theorem 30 is both ways, if you have the inverse, therefore your let's say if f now is the inverse, because it's playing that role here, f is playing the role. So by theorem 30, therefore g is bijective. Okay, so we proved this one just verbally. So okay, so g is bijective. All right, so that leaves proving that it's unique. How, in general, in pure math, what's the standard technique to prove that something is unique? Well, you typically assume that there's another possibility, like there are two possibilities, and then prove that those two are in fact the same. Like you may remember, quite a while back, we asked the question, does a group have more than one unit? So we assumed there were two, like E and E dashed, and we proved pretty quickly that E and E dashed were the same. Okay, so we'll use that same kind of reasoning here. So we'll assume that that there are two inverses for f, right? G and what is it? G dash or H? What are we saying? H. So let's assume. Okay, so we're trying now to prove the uniqueness that this inverse G is unique. There's only one, and if there were another one, H, we could prove that H actually is equal to G. All right, so let's try and do that. Let's see. So f maps from A to B. So G would be your inverse. So G maps from B to A. Okay, and H also maps from B to A. So we have these two inverses for f. G and H, both functions. We assume they're both inverses of f. And to prove that this G is actually unique, somehow we have to prove that G and H are the same. Okay, so that's what we're trying to do now. And if we can prove they're the same, then this G is unique. So then we can talk about the inverse of f. Right? So how to do that? Now, G is the inverse of f, right? So we've got something like this. So f f of g of b. They sort of cancel each other out. It just leaves you with b, right? And that's the same as f of h of b. Now, why is... I'm taking this from the textbook. Now, why is that? Okay, so here's your set A. Here's your set B. Here's a random point in your domain, and it maps to a point in an element in your codomain B, and you map it back with G, and you map it back. Map it back with H. Okay, that's the assumption. Now, here's your F. Okay, F. Now, what does F do? It just maps A into B, right? So F of A is B. We know that. We've seen that many times. Okay, so F maps A into B. And G of B, that's the inverse, takes you back, right? So if you apply G to B, you get back to A. But we're assuming there's another inverse, right? H. So H will also take B back to A. Right? Alright, so we're trying to figure out where this came from. Well, here's, f of A is B. Now you can put, so you've got A is this or this, so you can put that into here. You can put the G of B into here, or you can put the H of B into here. So let's do that, and you'll get this. So if I put this into here, I'll get f of G of B equals B. And if I put this one into here, I'll get f of H of B. Okay. Now what? How do I go about getting G and H out of that? Right? Let me just look at the textbook. Oh, I see. All right. Okay. So I've got f of something equals f of something else. Right? Now we know f is bijective. Right? We're given that. It's from theorem 1. F is bijective. Okay. Now if it's bijective, it is both injective and surjective. Now F is injective, right? Because it's bijective. Because it's bijective, it's injective and surjective. So let's just concentrate on the injective part. And if it's injective, f of something equals f of something else. It means the something else and the something are the same. Remember that? That was the standard proof technique to prove that something is injective. Right? So that means that whatever's here and here have to be equal. That implies then G of B equals H of B. Right? And that's, now since B is quite general, this is a general result for all B. All right? So G and H have the same two sets. So for G and H, this would be your domain, and that would be your codomain. So G and H have the same domain and codomain. They map the same way. The mapping's the same, because of this. Well, that means they're the same function, right? So G and H are the same function. So we've proved it. So therefore G is unique, right? therefore we can talk about the inverse, the unique inverse of f, provided that f is bijective. Right? That's from theorem 30. All right. So that's theorem 31. Now theorem 32. We move on a bit, and now we're going to talk about when you have three functions. And we then ask the question, well, yeah. So that's, we now have four sets, right? And that's function f, this is function g, and this is function h. Right? And we want to know these three functions, f, g, and h, are they associative? In other words, question. So h, g, of f of x, is that the same, question mark, as h, g of f? Right? So we've got three functions now. So we have this composite function, if you like, that would be h, g, f. Remember the order. So we're applying f first. So we map with f first, and then get the result, and then map with g, get the result, map with h, get a result. Okay. So if we map first g and then h, and that composite, well, we could call it k, or so gh, we just call it k. So is fk the same thing as, well, so we do f and g, f then g first. We could call that L, if you like. So, and then h. So